this is the International Workshop on Memory and Storage Computing at the ESWeek 2022. I'm Liang from East China Normal University. I want to know this workshop is sponsored by Scalability. Okay. First, I want to give a brief introduction to our workshop. This is the third year for this workshop. It's about memory and storage. Okay, so what is MSC? It means memory and storage computing. As you know, memory and storage has been widely developed during the last 20 years. But the memory and storage war is still there. So adopting the computing near or inside memory and storage become a critical solution to solve the memory well issue. So this workshop will gather researchers and engineers from the world and industry and academic to discuss this topic. So this is the program of this workshop. We have 2 half-days program, and the first day is include a keynote from Professor Hua Yu from Weichen University of Science and Technology, and then we follow with 4 high-quality invite talks from professors. And the second half day is tomorrow. Okay, I hope you're there. You're here and online. We have an industry keynote from Scalability. That is Zheng Ying from Scalability. Okay. This topic is very interesting. Okay, and we also have 4 papers, paper presentation in the second half day. Okay, we also have a poster section tomorrow. Okay, so you are welcome. Sorry. Okay, so this is the organization team for MSC. It includes Professor Yuan-hao Chang from academics in ESWeek, Taiwan, China, and Professor Weichen from Nanyang Technology University, Singapore. And the last one is me. I'm Liang from East China Normal University, China. And this year we have a program chair for the third year of this workshop. She is Professor Meng Zhang from Shandong University, China. Okay. Okay, so this is a very short open for our workshop, and let us go to the first half-day program of this workshop. So the first part is the keynote session. Is from our from Professor Yu Hua, Weichen University of Science Technology. Okay. Hello, Professor Hua. Are you there?
Oh yes. Okay.
Okay. Yes. I am ready to give a brief introduction to you. And
thank you.
So welcome. So the title of the presentation from Professor Hua is High Performance Learning Index in Disaggregated Persistent Memory Systems. Okay, I first give a brief introduction. Professor Hua is from Weichen University of Science and Technology. He was a postdoc research fellow in the University of Lincoln and a postdoc research associate of Manchu University. His research interests including storage system, power system. The most important part from Professor Hua is he has published the most number of high quality paper in this area, including OSDI, fast, micro, and everything you can speed out CSFA conference. Okay. They also have many academic service, including the PC chair in ICTCS, APCs, and also the PC member of conference. He is the distinguished member of CCF and the senior member of ACM and IEEE. He was selected as the distinguished speaker of ACM and CCF. Okay, let us welcome Professor Huang. Okay.
Okay, thank you very much.
You can go to the screen. Okay.
Okay, can you see my slides?
Yes.
Okay, thank you very much. Okay, so I think it's my thankful introduction, and it's my great pleasure to give a talk here. And I think this workshop is very good. And so this workshop, the topic is about the how to leverage the our current memory and storage to support the computing. So I think my today my talk is also tightly related with this talk. So my talk is to discuss the high performance lane index in the context of the popular persistent memory, and we also discuss the scalability. So in general, the lane index is a compute-intensive computer model. So this is the computing, and the persistent memory is to discuss the how to employ the memory benefits. So this topic is very naturally to match the topic of our MSC. Yeah. So in generally, we need to consider that a common problem is how to efficiently organize and index the data. So it's well known that we are in the era of the big data. So the data organization and the management is very important. But our memory, or even to discuss the storage hierarchy. So this is the hierarchical architecture. So we have the CPU, the high-speed cache, and the relatively large capacity memory. So this is a hierarchy. So in this architecture, we need to handle some issue. The first is that since we need to insert or delete the data, so this will introduce the dynamic data, the structure of the document, and we also need to provide service. In general, this is the query service. So, for example, to support the point or range query, and we also need to maintain or leverage some compressed approach to reduce the memory consumption. So we need to have a low overhead for memory footprint. Since we are the computing, in general, the processor is multi-core, so we need to we need to support the high concurrency to exploit the benefits of the multi-core processor. But currently, we generally leverage the B tree or B plus tree to handle this issue. But in general, it's well known that we can the B tree can support the dynamic tree balancing, but it's inefficient to support the query due to its high penalty among of the pointer jumping among the multiple level in the hierarchy. And we also need to have maintain the metadata to such as the pointer address or the relationship among the multiple level. So this will be also introduce the storage consumption to maintain the multiple inner node. Since all data is maintained in a query path, so it have the high dependency. So this will be introduce the side effect to introduce the high dependency that will be decrease the performance. So in this case, that we need to have a high-level consideration that what's the main role of the index structure. Okay, it's need to we can consider it's a function. Is have the input for the period data, and output is the position of the period data storage. So this means that this inside the structure should be sorted data, so we can then to improve the query performance. But this generally idea will be suffer from the latency and the memory footprint, such as we have just mentioned, that is constrained by the memory jumping, and also consider the multiple level nodes. So this will be also introduce the computing and the complexity. But we can have a new consideration or new viewpoint to consider the index structure, such as we consider index as a machine learning model. So this will be actually this idea is to explore the local computing to replace the remote I/O read out write. So this is the general idea. I think this will be very efficient in the currently hierarchical memory or storage architecture. The reason is that why the storage or memory performance is constrained by the many memory or storage device. The reason is that we need to read or write, right? We need to consume some latency or throughput in the I/O bus. But if we can execute some computing in local cache, so this will be reduce the requirement for read or write. So this will be also need to avoid some data movement or some potential snooping, fast snooping, right? This is also a security issue. So this is the basic idea of the index. Index is to consider that in the index not a disk structure but a regression model. So if we will query, we can traditionally for query we need to consume some read or write through the I/O bus to read the data or write data for the low speed whatever for SSD or disk to get the query result. But the index consider that we don't need to read or write. We just to compute the query result. So this will be exploit the computing capacity of the multi-core processor, and also to reduce the or even to avoid the data movement. So in the context of the index, we can consider the index is a regression model, and we compute is approximate position. Of course, this is a range. We have a max. This is a range. We have the lower or upper bounds, and we see this range. We can get the query result. So this is a very basic and efficient idea, and we also need to handle that. The first problem is how to identify this model. So we need to learn from the CDF to improve its high accuracy. So this is the right part figure. We can learn different data set to get the accurate model. So in order to improve the entire index performance, we need to build a ecosystem for the index. So in this talk, I would like to introduce some recent work in our group. The first is to improve the scalability of the index itself, and we also identify that it's not very efficient to just to improve the index itself, and we also need to build an ecosystem for the index. Not only about its the lower level is infrastructure, and also is to improve its reliability and also the security. So our then goal is to provide a efficient ecosystem, including its high performance, reliability, and security. So in generally, that what we have discussed is to focus on the index in a single node context. But as we know that in generally, our storage, our memory system is a distributed system. So it need to include many servers or many nodes. So we need to consider that how to improve its scalability. But the first issue is that as we just mentioned, for the index, if we insert or delete some data, so the model will be changed. So we have to do the model retraining. So the model retraining is the computing intensive task and also consume many systems resources. So we need to efficiently handle the first problem to the retraining to efficiently insert new data. Since this index is the sorted structure, and we need to keep our data sorted. But as we know that sorted is very expensive, right? So we also need to efficiently keep our data sorted to support the queries. We also need to consider that how to efficiently exploit the benefits of the multi-core processor. So for read, write, or even the retraining. So this operation in general mixed, but we also need to support the concurrency. So this is the one challenge we need to handle. In the meantime, that we know that in general the index is contains two parts. One is the computer part. The computer part is multiple level the models. So different models also have some data dependency, but data dependency we also is the performance is constrained by the query from the top to the bottom, and then we can find the query position. We also need to, in generally, if we insert a new data, but the new data may be an outer layer. I mean that it may be located outside the predefined range. So in this case, that we need to retrain the model. So in this case, that how to efficiently process the insertion is also become very important. Existing work also aim to address, as mentioned, the challenge that but it will be also suffer from some high overhead. For example, we can build a dirt buffer. The buffer is a very generally or common structure in the storage or memory systems. We can build a dirt buffer to temporarily store the new search, and we can build a temporary structure and then to flash the sorted data to the index in a batch. So this will become very efficient. But this will also suffer the problem of that this data may be not efficiently sorted, because that the buffer data is just the partial data, not the full data. So this is a sorted order maybe become not efficient. So we have maybe we also need to sort the data in the index. Another case, issue is that depending on the buffer size, if we build a large buffer, so this will be decrease the performance, since that this will be introduced the more searches operation. Another issue is that we have just mentioned that different layer also need to maintain the dependency. So this will be also constrained is concurrent performance. Other efforts aim to, for example, to preserve some empty slots. The empty slot means that in the retraining, then we can temporarily insert the new data into this empty slots. But this will be also introduce the memory inefficiency, and we need to recontrain because that the data dependency will be also decrease the concurrency issue. So this will be also introduce the long latency and decrease the overall performance. In order to address this issue, so we propose the fine-grained index structure. And in this structure, we classify the entire operation into two parts. One is the model part, the other is the data part. For model part, we aim to training the independent model. So it will means that the models will become that independent. So we can mitigate the dependency and improve the system performance. The other is the data part. Data part aim to address that the high complexity for query. So we build a flattened data structure. You know that the flattened data structure will be reduce the data dependency. And all these two parts are work together to support the two granularity concurrent retraining. So this will be efficiently handle the new inserted data. Before we go to details, we can handle that the model to improve the model accuracy. So this means that we leverage the recursive model index. So this will be we have examined many data sets to identify that if we have some new insight to be used for improve the index. So we can observe that even for in the same data distribution, different the model accuracy will also become the errors. So we need to carefully handle this model accuracy. We also observe that even we use the different learning effects also become the errors. So it will be existing design scheme built to efficiently learn the data distribution because that the performance it have no very clearly pattern. So we need to efficiently handle that the training operation to learn from the data distributions. So in order to address this issue, we build the first build the for the data part. Data part means that we need to guarantee that no data loss. So this you mean that in generally we will for new inserted data, if the data is out of range of the predefined range, so this will outlier maybe loss. So this need to be avoided. We also need to guarantee all data are sorted and to reduce its dependency. You know that if we reduce the dependency, so this will improve the concurrency performance. So we build the level bins. Level bins means that we build the flattened data structure, and we can easily append the small size level bins behind each trained data. So if we insert a new data, so this will be can easily append the current the data item. So this will be improve its memory space utilization. For the training and exploit the multi-core processor performance, we need to improve the retraining performance. For in generally, if we need to do the retraining, we need to this operation can be divided into some sub-operations, such as including the we need to merge data, resource data, and retraining the new model. So this three operations need to be completed for the retraining. And we observe that in generally, if we for the older model, this is the timeline, right? So for in generally, if for the non-concurrently model, before we do the retraining, so this operation need to be blocked, and so the common operation will be affected. So in order to address this issue, we support the concurrently operation. That means that before go to this new model, that this will be also introduce the this loss, so we can carry out this operation in a concurrently manner. So we aim to address this issue. We classify this operation for data into two granularity. This means that we can do the level bin retraining and the model retraining. So for level bin retraining, we retrain the full level bins, and other trained data of level bins are not blocked. So in other words, that for model retraining, we can merge some small models. So these models can be carried out in a batch. So this will be also performed in background. So this the general or common operation will cannot be blocked and no effect. So when we all these mentioned issue can work together to carry out the operation, such as to update the corresponding value point and insert the data into the level bins. And we can also support the delete to, remove the data from the level bin if the users aim to delete this query data. So we examine the performance in the real test bed and compare with the state of our work. And we also provide the open source code. And we can observe that even for the heavy writes, our purpose scheme can also improve the performance, especially for insert operation. So we also need, we have discussed is to build a scalability for the index, and for its infrastructure. The index need to provide a large capacity memory and high performance I/O, and this I think is the strength of the persistent memory. So I think persistent memory is widely known that it have the non-volatility and high performance, and to also to support the high performance system operation. So we consider that in generally that the persistent memory is discussed in a single node, but currently we have new system models that we to disaggregate the model to separate the computing and the memory and the storage resource into different pools. So this will be, I think, will become very cost efficient, especially for industry. So we changed the traditional memory disaggregation to decouple the monolithic servers into different pools, including the compute pool and the memory pool. And all these pools are connected via the RDMA network. So I think that even for the computer pool, it does not mean that it only contain the computing whatever for CPU or GPU processor. It also have some small DRAM cache. So this will be for improve the performance as a buffer. And also for again for the memory pool, it does not mean it's only contain the different memory device. It also have some weak computer units to handle some basic operations. So if we discuss the divided the memory system into the disaggregated model, so it can improve the resource utilization and to efficiently handle the crash consistency. In this case, since that we changed the model from a single node to the distributed environment, so all this operation will be carried out via the network. So the transaction will become very important. So especially for the distributed transactions. And in the context of the memory system, we need to handle the transaction. Transaction means that operation will become the atomic, which means that this operation need to be complete, will be complete or not, right? Is that's the 1 or 0, only 2 status. So in this case, that if for the distributed transactions, we also need to maintain that different servers, and these servers will be handled via a centralized coordinator, and all operation will be carried out via the network. For So in general, that one very popular network is the RDMA-based distributed transaction. So existing concurrency control have been proposed to improve RDMA performance and to efficiently allow the operation among the coordinator and the different servers. But we also, since that all these servers need to guarantee the reliability, so we need to provide the backup for the primary servers. So this will be introduced more RDMA operations. So this is based on the prime backup replication model. And if we discuss this guy with precision memory, so we consider that one-sided RDMA. One-sided RDMA means that the most RDMA operation can be handled in the memory controller and also involving the local CPU. So this will be also further improve the performance. And in the local computer pool, is maintain a small DRAM cache. It can maintain the some small data. I mean the metadata and the query result. And if for the present memory pool, is maintain a weak computer unit. It's just do some basic operation such as the allocation or connection, but not involved with the complex transaction processing. But in this case, we also need to handle some challenge. The first one is that since this operation will be completed via the network, so we need to have to handle the many round trip. For example, for the one coordinator and the one A, B, C servers, it also have the prime and backup. So in order to carry out some operation, we need to have the execution, locking, validation, and finally complete the backup, and finally complete the primary. So this will introduce the 5 RTT operation. So and even we consider that all operation will be carried out in the distributed environment. So this will introduce the high costs. The second challenge is that the precision memory, the bandwidth is limited. So we know that the popular RNIC operation is much larger in the local precision memory. So in this case, that if we apply some operations such as the redo log, so the temporarily stored data cannot be read, since that the primary PM is much slower than the primary RNIC. So this will be become the bottleneck and slow down the entire system performance. The third challenge is that we can all in the distributed environment, we cannot guarantee that a data, I mean that it's flushed into a remote the replicas if it's really be stored in the remote replica. For example, if we write the data from the coordinator to the replica, and the data file is temporarily stored in the memory controller, but you know that the memory controller is only contain the volatile buffer. So in this case, when the data is flushed into the volatile buffer, the coordinator will receive a ACK acknowledgement message. That this is very fast, very efficient. But we cannot guarantee that if the data file is really be flushed into the non-volatile device. For example, in this case, if there is a system crash or power down, so the data will be lost. I mean that is just being read into the memory controller, but not to the persistent memory of device in the replica. So this will introduce the inconsistent issue. But coordinator cannot aware of this issue because it have already received the ACK message. So in order to address this 3 challenges, so we proposed some efficient technique, such as first to reduce the number of round trip, and also to do the load balance, and to carry out the remote consistency that will introduce a low overhead. So in this case, that for client, and we have the compute pool and the persistent memory pool. And then we first allocate the memory and load the table and build the connection between the compute and the persistent memory. When the client issue the transaction, we leverage the one-sided RDMA, since that this cannot involve the local CPU and become very efficient. And the coordinator will complete this operation, and we build the transaction processing library and in the PM pool to use the index structure. So this is the entire overview for our proposed scheme. So the first thing is that we leverage the efficient logging. So this means that we can read and log the read and write sites when executing the operations. So this logging means that we can merge the operation together. So this will be carry out the operation in a batch. I mean that the operation does not separate to be carried out. So we can use just a one round trip to complete the validation. The second proposed technique is to we can commit our replicas together in one trip. So in this case, that from this figure, it's much clear that this operation can be carried out in place, and we can prevent the reading partial updates. So this, if the data is visible, and we can flash the data replicas that's in one RTT. We also, in order to allow the backup to backup servers, that we have the primary and the backup servers. So for backup servers, we can support the read-only data, right? So backup just provide this service, that's enough. And we carry out the in-place update, so there is no need for the address redirection, and we support the undo log. So this will be it's not easy to without the data migration and without the local CPU to carry out the verification operation. When in order to improve the system performance from the remote flash operation, and we carry out the efficient remote flash. So this will be, that traditionally for a single server, we have the flash or CLWB CPU instruction that can guarantee that the data from the CPU can be safely flashed into the local PM. And for, in this case, we propose a remote flash. That means that we guarantee the data can be safely flashed from the coordinator to the remote servers. So this will be, by using the selective flash, we can also reduce half of the round trips. Put out proposed scheme together, we can observe that for execution, since this data is merged, and we just need to one operation for validation and the selective flashing operation. So all this operation can be reduced to 3 RTT. So this will be reduce the network consumption. And we also evaluated the performance and compare with the state-of-the-art scheme, and whatever for the end-to-end performance, we can achieve the system improvements. All we have discussed is to discuss the index is require the high performance, and we also know that for a general system, some servers will have to face the system crash or power off. So we need to provide a reliable infrastructure for the index. So one critical issue is the bugs. So you know that we have built the index hours of persistent memory. So the software have maybe generally have the bugs. So we need to handle the bugs. But in the context of the persistent memory for index, this will be, since that persistent memory can naturally support the multi-core processor. So the concurrency operation is generally metric. So we need to first handle the concurrency bugs. In generally, for the persistent memory programming, we have the just remember that we have the volatile domain that have the CPU cache and also the DRAM, and we have the persistent memory. And when we write the data, right? So if there is a system crash or power off, the data will be lost. But in the persistent memory, we can guarantee that the data that will be safely flash into the persistent memory. Maybe use the CPU instructions. But if but you know that in generally the persistent memory programming also need to face the out of order CPU. You know that for programmer we write the data is have a execution order, but actually in order to improve the system performance and improve the resource utilization, the CPU when CPU execute the program, this will become the after order. So for example, if we write data the x and y, but actually maybe carry out in the order of y and x. So in order to guarantee that the program execution in order, so we need to add some fence. So this is well known as fence, right? So we need to guarantee that the data needs to be carried out in different domains. But if for persistent memory, this problem will become more challenging because that we need to maybe we become face that the missing flash and the fence. For example, if we write the data x and y, if there is a system crash or power off, you know that the original data have been maintained in the persistent memory device. So when system is a restart, okay, so we need to maintain the partial state or the intermediate state, not the final states. So this will be introduced high cost. So I mean that in this case, the flash and fence will become the for programmer. We need to consider that how to add the flash and fence in the PM-based programs. This is the correct is bugs due to that the lack of the flash and fence in order to guarantee the consistent data. I mean the crash consistency. Another issue is that maybe we need to add some flash and fence, but this maybe will become that redundancy. You mean that for a programmer in general is I mean in general, frankly speaking, a programmer cannot actually determine that if we need to add a flash or fence. So for safety, we can add we need to add the flash or fence. So this will be introduce the actual flash. Actual means that this will be decrease the system performance. So in order to not only to address the correctness bugs of the performance bugs, there are also some patterns that may be related to the application specs bugs or the cross failure risk. So this is also all this consideration means that don't consider the concurrency execution. I mean that no consideration for the concurrency bugs. In generally, but in the persistent memory context, the concurrency is still important to the persistent memory performance. And for example, if we carry out two threads, thread 1 and thread 2, if we flash the data from the CPU cache, and we can safely flash the data from the CPU cache to the persistent memory. But you know that the program is executed maybe after order, right? So in this case, that if there is a SIM crash, the X is not flashed, right? So in this case, that the Y and the X will become inconsistency. So this means that even the concurrency is visible, but this also means that the data is really persistent. So in order to address this issue, we explore the interleaving and to consider that the possibility of different threads. For example, for thread 1 is M instruction, and for thread 2 there are N instructions. So this interleaving will become exponential increase, right? So in this case, but there is a bug. This will be as we have just mentioned the example. There is one possibility for this bug. So in this case, this will be very challenging that we need to identify the bugs in the space of the exponential interleaving. So this is very difficult. Another challenge is that we need to handle the false positive. False positive is that we may report a bug, but actually it's not, right? So this will be due to many reasons, such as inaccurate checker. Our system already have completed the recovery. So we also need to try to avoid the false positive. And our proposed scheme is the persistent risk. This means that we can handle the concurrent bugs in the context of the persistent memory. Our basic idea is to handle the first is the inter-thread inconsistency and to avoid the synchronization inconsistency. And our use the tool is fuzzer that can efficiently handle the coverage-based fuzzing, and we leverage the post-failure validation to avoid the false positive. And our initial result is in existing 5 concurrent PM programs, we can identify new bugs. The basic idea is that if there are 2 threads, thread 1 and thread 2, if we read a non-persistent data, so this will be introduced the ret data and flush the data Y. But this will be, you know that as we have discussed, different threads will be introduced the interleaving bugs. And we explore the real-world case. For example, in the PCLHT, this from the RESIT. This is a open source code, and this idea is to use a trained high table for in the context of the persistent memory, and it's use the log-free read and bucket grind logs for that. You mean that for log is just a log 1 bucket, so this will be efficiently support the concurrent operation. But for its code that we identify concurrency bug, and this is due to the inter-thread inconsistency, and this has been verified, and this operation will be also introduce the loss. And in this case, that we consider that the durable satisfaction, and this satisfaction comes from the another thread. So in this case, that the synchronization inconsistency will be can be avoided even by using the restart operation. This operation can be avoided that we can block always on the bucket. So this will be further improve the system performance. And we also use the PM-based inter-thread inconsistency method. So this can avoid the cross inconsistency issue. We use the real-world persistent memory codes for evaluation, and we identify the new bugs. This means that the persistent memory concurrency bugs in the real-world applications. The final topic in my talk is to discuss the security issue. I think that this is also important to not only for persistent memory, also for maybe our non-volatile memory system, because that traditionally if we need to guarantee the data security, we need to increase the data in the DRAM. But if there are some system crash or power off, okay, so the data, I mean that the source data have not been encrypted, will be lost due to the DRAM is the volatile device. So there is a data loss, but no information leakage. But for if we use the persistent memory or non-time memory, so in this case, that the source data that have not been encrypted will be still maintained in the memory device. So this will introduce some security issue. So I think that this is also important if we deploy the non-time issues, non-volatile device into a larger scale. In generally, that we consider the persistent memory. This is considered like two parts. One is the we know that this is the volatile part. This is we have the multi-core, multiple level cache. All this operation can be handled in the memory controller, and by using the through the memory bus, they can write the data into the non-volatile persistent memory. So in this case, that one issue we have just for the security issue. This is involve the encryption or decryption for data. The other issue is that crash consistency. Crash consistency means that for the persistent memory, essentially just maintains the temporary or the intermediate states. I mean, not the final states. So this will be introduced some data consistency issue. I think this topic have been widely discussed in the community. So for security consideration, we classify the memory hierarchy into two parts. One is the trusted, and the other part is the untrusted. So if the data is moved from the on-chip part, and the other is the persistent memory, maybe suffer from the physical attack, such as stolen the DRAM attack. As I remember, I give the example. If the data, I mean the source data, have not been encrypted in the persistent memory, they can be moved to another machine and get the data. So in this case, that we aim to consider that how to efficiently use the index in the memory hierarchy. You know that the key issue is that the data, traditionally the data need to move from the cache into the persistent memory. So we use the length index in the memory part, in the cache part. So in this case, that we can locally compute the query result, not to read or write data through the I/O bus. So in this case, we can naturally avoid the bus spoofing attack. So this will be very efficient for the PM security issue. But you know that we can avoid most of the data movement, but cannot fully avoid the data movement. So we also need to have some small fraction data read or write through the bus. So in this case, we also need to carefully consider how to guarantee persistent security issue. The first one is that we need to guarantee the confidentiality. That in order to guarantee the concurrent operation, we leverage the counter mode encryption method. So this might mean that for query issue, that we can use the XOR operation. It means we can input its physical address, the key, and the counter. We can generate the OTP, I mean the one-time path, and the OTP operation can XOR with the separate text. So this will generate the plain text. Or else, if we use the plain text XOR, so to be can encrypt data to generate the separate text. So this will be can carry out in parallel with the general operation. So in order to avoid the potential attack, that we also need to guarantee is integrity and to avoid some potential tamper attack. All this data in the context of persistent memory this is the security issue. We also need to guarantee it's an integrity issue. I mean that we need to avoid some modification to become the attack to the entire operation. So this will be introduce the BMT. I mean the Merkle tree. This will be easily identified which data have been changed or modified. So in this case, we need to not only to guarantee the security, but also to guarantee the integrity. So in this case, we need to we use the counter cache to guarantee the security and the BM cache to guarantee the integrity. And we maintain the data. If there is an update, we can safely from the CPU cache to the persistent memory. And in generally, only data is persistent. So this will be cannot safely decrypted or verified. So this will introduce the inconsistency. And for the counter cache, it cannot be flushed into the persistent memory in the same time, since the CPU instruction, such as the CLW or CLFlush, can only guarantee the CPU cache, not the counter cache. So this will be also difficult to be verified. So also introduce the inconsistent issue. And for the data MAC, this MAC means that for the integrity verification to double check if a data is be attacked or changed. So in traditional architecture, it's also difficult to be decrypted. Another issue is that since that the L bus is limited, so generally it's much smaller than a cache line. So this will be introduce the partial updates. So it's still an inconsistent issue. So we in order to address this mentioned problem, we propose the failure automaticity scheme. The basic idea is we can group the read data and to flush data in a batch, and also to integrate the data counter and the CMAC together. So this will be bridge the gap between the security issue and the integrity issues. So we built the durable transaction and with red hat logging. This is the entire architecture, and we have three parts. The first one is to leverage the read-through security data cache and to guarantee the BMT update to be carried out in the background. The second is to build a transaction-specific epoch persistent model. So this will be minimize the outgoing constraint between the logs and data. The third part is to build a security metadata rate reduction. You know that persistent memory will be suffer a limited lifetime, so we need to try to reduce the number of writes. So for the read-through issue that we consider issue by using the logging, and whatever for the local region or disk region, we can guarantee its consistency. And in time for BMT update, this operation for integrity can be carried out in the background. So this will become faster. For the read-through security metadata cache, we write the we use a CMAC address to record its physical address and to track easily track its counter bit map and build the counter block. The CMAC is generally major can include the minor and major counters, so this can be easily and to avoid the counter overflow issue. And we also build the persistent model to support the both the security and integrity. And the idea is very simple, that we transform the traditional independent write operation into the merged operation. So this operation can be carried out in a batch. So in this paired epoch, additional epoch can be paired, and we can merge the carry out the released operation together. So this will be also to minimize the outgoing constraint. this proposed model have been implemented in the TEP context. In order to reduce the number of writes to the persistent memory, we collected the log and the counter. So this will be also reduce the number of counters. In generally, one counter corresponds to one ID, right? One log, right? So in this case, we can merge the shared counter together. So this will be also reduce the number of writes. This can also easily carry out in the context of the BMC tree. So this will be place the log and data. We also carry out the evaluation and to examine the real performance by using the well-known benchmark. And our evaluation shows that we can not only guarantee the security, but also to improve the integrity by a low cost and overhead. So our my talk is to aim to introduce the learning index that is essentially to exploit the local computing to mitigate the read and write through the expensive I/O to the memory expensive, but it also need to build a ecosystem for the index application by using the important infrastructure, including its high performance, reliability, and security aspect. That's all. Okay, thank you.
Okay. Okay. I think this is the talk from Professor Huang. Any problem from online or offline? You can unmute.
Hello, Professor Huang. I have a simple question. Thanks for the nice talk. I think in your first work, you mentioned you have some fine-grained models to store I think the mapping for the learned index data. I wonder how many models do you have, and do you need a large space to store the models themselves?
Okay, I think thank you for this question. I think this is a very good question. In general, this will depend on the application requirement. For example, if for some general case, this will be several megabytes. For example, for generally indexing, for example, to support the point of range query, and this the number of model will be determine the query accuracy. For example, if you aim to for high accuracy, you need to use more models, right? But this will be actually will require more memory space. But in general case that if you aim to relatively acceptable accuracy, so this will be reduce the number of models. So I think this will be in real world case will depend on the application requirements. Okay, thank you.
Okay, thank you.
Okay. Any more question from the offline online? Okay. Hello, Professor Huang. I have a very short question for the overall presentation. You're working on persistent memory. You have no Intel has stopped the production of persistent memory. So do you have any comments from the academic side? Yeah.
Okay, I think this is a very good question. I actually, frankly speaking, I have no very confident answers, but I just show my some opinion for your consideration. I think that persistent memory is a very good research direction. You know that traditionally, what we consider for the computer architecture, what's the memory need to offer? I think the 2 points. One is the high performance, the other is the non-vulnerability, right? So this in this case that the persistent memory can use just one device to provide not the high performance and the non-vulnerability. You know that traditionally we leverage the memory DRAM and SSD or even disk multiple devices to provide this operation. So I think this will be very interesting and very promising research work. Yeah.
Okay, thank you. Any more questions? Okay. I think the time is to the end of the keynote. So we have prepared a thanks card for you, and since you are online, so we cannot give you now. I will take a picture for this, and Professor Chang can you help to take this for to take a picture for yeah. Okay. Professor Huang, could you stop your stop the sharing and screen share?
Okay, yeah.
And we will give you the stamp card with you. You are online. Okay.
Okay. Thank you very much. Yeah. Okay. Thank you very much. Yeah.
Okay. Thank you, Professor Huang.
Okay. Thank you very much. Thank you.
Okay. So we're ready for 10 minutes break. So just go outside and take some snack. Okay. Coffee. Okay.
Okay, so we come to the next session. We have 4 high quality invited talks here. Let me introduce the first speaker. The first speaker is Professor Xiaoyong Xue. Professor Xiaoyong Xue receives a PhD degree in microelectronics from Fudan University. He is now an associate professor with the National K Lab of Integrated Chips and Systems and the School of Microelectronics in Fudan University. His research interests include high-performance memory storage, in-memory storage computing circuit and system. He has published more than 100 peer-reviewed papers in ISSCC, GSSC, IEDM, Symposium on VLSI, Nature Electronics. He has co-authored 3 books and has been granted more than 10 patents. So Professor Xue will give the talk of prospects of computing in memory in future data processing architecture. So welcome, Professor Xue. Can you share your screen?
Okay. Thank you. Can you see it?
Yes, I can see your slides.
Hello, everyone. I'm Xiaoyong Xue. I'm from Fudan University. Today, I will give a talk about prospects of computing in memory or storage for data for future data processing architecture. This is the outline of my talk. First, I will talk about the concept of computing memory or storage. Then I will give several implementations. Then the industry, I will talk about the industry of computing memory or storage. Finally, I will talk about the prospects. First, I will the background. As we all know, artificial intelligence is changing almost every aspect of our life or work. AI also calls for very high performance and power efficient computing chips. However, as we all know, the mouse now is slowing down, and the gains from device scaling is becoming smaller and smaller. Besides, the AI applications are often data intensive, which makes the Neumann bottleneck become prominent. Let's explore the volume bottleneck further. In the computing system, the memory is organized in a hierarchical way. At the top is a CPU, and the SRAM is often embedded in CPU in the form of cache. Then the DRAM and SD. If we carry out a computation, the data is often loaded from the lower storage or memory to the computing processor. The power of data transfer is often much larger than that caused by the computing. Then we may think about, can we move the computing into the memory or near the memory, or can we move the data to inside the computing device or near the computing device? The answer is yes. First, let the data near the computation be near the computation. It is here there are several ways to implement this. Firstly, for the CPU chips, the cache is becoming larger and larger, which can store more and more data. Other ways, including HBM, high bandwidth memory, or HMC, which they both can shorten the distance of data transfer. There is also recently there is also another way, chiplet, which by using advanced packaging techniques. However, these techniques are still based on the architectural volume. The memory and the memory and the computing device are still separated, and the data is still need to be transferred from the memory to the computing device. The second way, let the computation be close to the data. It is in fact the computing ability can be integrated in all the layers of the memory hierarchy. For the cache level, we can embed the computing function in the SRAM or embed the volatile memory. Also, we can customize the DRAM controller or its internal circuitry to support the computation. For the SD level or storage level, we also can customize its controller or internal circuitry to support the computing function. It is important to choose the right type of computation, because for the lower levels of memory or storage, the speed is usually smaller. Before we talk about the computing in memory storage, it is necessary to clarify computing in memory and the near memory computing. The computing in memory is usually refers to the computation is carried out in the memory array and then post-processed in the peripheral circuit. The near memory computing refers to that the data first fetched from the cell array, then processed by the peripheral circuit. In fact, both can be defined as computing memory or storage, since the peripheral circuit is part of the memory or storage device. Now let's go to the second part, the implementation of computing memory. In this part, I will first talk about the SAM applications and architecture. Then I will talk about the SAM based on embedded memory. Then SAM based on main memory or storage. Because the computing memory is usually suitable for performing matrix vector products with very high parallelism. So the SAM application usually has better prospects in machine learning, crystallographer, or solving differential equations. For the implementation, it can take the current-based SAM approach or charge-based or fully digital approach. There is also another approach, time domain based. We can see the different approaches will bring different characteristics. Now let's look at the several key peripheral circuits for computing memory. The first one is the ADC. ADC is very important for current in memory computing memory, because the computing in memory is often performed in an analog way. We have to use the ADC to quantize the output. Then the results can be used by a digital part. The other important computing circuit is the DAC. DAC is used to represent the activation or the input of the SAM part. For ADC and DAC, the accuracy and the precision is usually both very important, because the SAM, the precision of SAM is usually dependent on ADC and DAC. There is another important circuit, reference and summation circuit, because the computing memory is usually formed in an analog way. So we have to develop the very accurate reference circuit to differentiate the results. Now let's look at the SAM based on embedded memory. In fact, almost all the memory devices, including SRAM, embedded long-volatile memory, and EDRAM and flash can be used in computing memory. Among all the memory devices, SRAM usually uses a standard CMOS process, so it is better. So SRAM-based computing memory can be used in SoC design with most advanced process. Here are several SRAM cell structures for computing memory. The first type is current-based. It takes standard 60 SRAM cell structure, but it may suffer from the destructive rate problem. The second cell current type is the 80 SRAM cell. It uses decoupled rate pass, so it will bring the benefit of non-destructive rate. The second type of SRAM cell is charge-based. We can see for the charge-based SRAM cell, the bit line are first pre-charged during computation. Then the result will be dependent on the discharge of the computation result. The second charge-based SRAM cell is based on the local capacitive coupling of a local SRAM cell, then it will use a charge sharing method on the baseline to realize the summation operation. For the networkers, we can see from the recent ICC papers, the precision of the network supported by CM is becoming higher and higher. Also, the application is also getting more and more complicated. One thing we should pay attention is that these accelerators often support part of the computation of the neural network, since the array capacity is usually not very large. SRAM CM also can support other functions like specific logics. We can see when we activate two rows, we can realize the AND function and an OR function using different references. The CM based on embedded laboratory memory is similar to that based on SRAM, because the embedded laboratory memory usually takes the form of a variable resistance. So it usually uses the crossbar array architecture or 1-to-1R crossbar array architecture to realize the CM function. Apparently, the crossbar architecture has a higher density than SRAM-based one. We can see that EDRAM can also be used in CM because, in fact, it's similar to the 1-to-1 or 1R or the 80 SRAM cell. The data is stored in the form of charge in the storage node. So this transistor will function as a read transistor. But EDRAM will call for the refresh operation during the computation. The accuracy of the computation may be impaired by the leakage of the storage node. Here I will point out the 3 important challenges faced by CM based on embedded memory. First one, as I mentioned before, the capacity of the memory array is usually small. It will be difficult to hold the large volume of parameters in the small array. So we have to find some mechanism to update the memory array or increase the memory capacity. Secondly, the computation efficiency, also the area efficiency or the energy efficiency are seriously affected by the highly costly ADC or DACs. We can see for a CM module, the ADC and DAC part will often takes more than 50% or 70% of the total. Finally, the accuracy is usually seriously influenced by the non-identities of the computing devices, because the CM is usually performed in an analog way. The efficiency of the analog computing will influence the accuracy of the CM. Now I will talk about the CM based on main memory and storage. There are a lot of people working in CM based on embedded memory. Also, there are also a lot of people working on based on the CM based on main memory or storage. Here, I will talk about the CM based on the main memory and the storage. There are many approaches to implement this. First, customize the controller. For the main memory, also the DRAM, we usually embed the computing components in the RCD die, also the register clock drive die, or data buffers to realize the computing in memory. For storage, also SSD or NAND flash, the computing in memory is usually implemented by embedding the computing function in the controller. For both main memory and SSD-based computing memory, the major challenge is to find the killer application to make the computing memory really and very attractive. Another approach to realize the computing memory and the storage is to customize the memory or storage itself. For we all know that DRAM and NAND flash are manufactured by the foundries, and we can most of the users cannot take part in the design of the DRAM or NAND flash. However, in the future, it may be possible. In fact, the foundry itself is doing something like this. For DRAM, they are replacing some of the banks or integrate or change some of the peripheral circuit to realize the computing memory. For storage, we can see some foundries like Micronics and is changing the circuitry of the NAND flash to realize the computing memory. We also see some industrial support from the industry. In fact, the computing storage or memory is becoming the standardization is becoming possible thanks to the support from the industry. We all notice that the MME Express also has a group on the standardization of computing storage. Now let's look at the industry of computing memory storage. In fact, the computing memory is not the industry has a lot of interest in computing memory, but currently there are almost no products from the industry. Their effort mainly lies on the research currently. We can see the TSMC is doing some CM work in ISCC. But they take a digital approach instead of an analog approach because the analog approach may be not stable. For the DRAM, as I mentioned earlier, the Hynix and the Samsung are both as two bigger DRAM foundries. They are changing their DRAM design to incorporate the computing memory function. Currently, they are mainly based on they are mainly targeted on they mainly target at the machine learning acceleration. Also, there is also interesting work from the Intel and the University of Texas. It is EDRAM based computing memory, and it is research work, not and I think they may have a lot of they may need a lot of effort before commercialization. For the computing storage, the industry is also making some effort, mainly from Micronics. We can see Micronics published a lot of papers by changing their NAND flash design to incorporate the computing memory function. Also, the Samsung is also doing some similar work. It's good to see that there are some startups working on computing memory, like Weichen in China and Mystic abroad. They both use embedded flash because flash is relatively mature. The target application are both machine learning acceleration. Finally, I will talk about the prospects of computing memory or storage. First, I think that in the future, the computing memory will first and mainly be used as an integrated accelerator on SoC, because the CM function is not a generic computing device. It has to work with other IPs or the CPUs or processors to realize full function. Secondly, I think in the future, NAND and DRAM will be customers, will more and more be customers by the users.
Hello, 5 minutes. 5 minutes.
Oh, okay. Thirdly, I think in the future, neuromorphic computing may be a good method to realize maybe a good application for computing memory. Because computing memory resembles our brain in the form of the distance, in the form of that the distance between the computing device and the memory device is small. Okay, this is my talk. Thank you very much.
Okay, thank you, Professor Xu. Let's see whether we have questions from the audience. You can just unmute yourself. Okay, we see a question from the chat box. So it's mentioned that CRM can be implemented based on different memories, such as SRAM, DRAM, IRAM. Which one do you think is the future, please? Thanks.
I think because for the embedded memory, SRAM is standard logic based, standard process based. I think for the most advanced technology used chips, SRAM will be the first choice. But for other not very advanced technology, the embedded memory may be a good choice because of their higher density.
Mm-hmm. Okay, thank you, Professor Xu. Okay. I think due to the time limitation, we can have further communications offline, and we also prepared a certificate for you, Professor Xu. Yeah.
Okay, so thank you very much.
Okay. Hi, Professor Xie. We also have this one, and we ask Professor Chang, can you help to share this? Yeah, this card. Okay. Okay. Hello, Professor Xie.
Hello.
I'm so sorry, I cannot give you on hand.
Okay. Yes, it's very good. Thank you very much.
You can share a screen for the first slide.
Okay.
Okay. Thank you. Thank you.
Thank you.
Okay, thanks again for the nice talk. So now we can move to the next talk given by Professor Chundong Wang. Professor Chundong Wang works as a tenure-track assistant professor in Shanghai Tech University. He received the bachelor's degree from Xi'an University and the doctoral degree from National University of Singapore. He has published a number of papers in TC, TDSC, TOS, TCS, and so on. His research interests include data storage, computer systems, and security and privacy. The talk given today would be exploring the implications of memory and storage systems to boost the performance for applications. Okay, thank you, Professor Wang.
Yeah, thank you, Professor Zhao, for the introduction. Hello, everyone. I'm so glad to have this opportunity to share what we have recently done with the memory and storage system to boost the performance for key-value stores, mainly for today's talk. We all know the software and the memory hierarchy, they need to collaborate together to provide the support for the application. We have the software layers. As you can see here, we have the applications like the key value store I will talk about today. They are working on the operating system, and the whole software is on the memory hierarchy, as Professor Hua and Professor Xue mentioned. So with this memory hierarchy, I will mainly talk two points today. One is on the I/O path between the DRAM, the main memory, the DRAM maybe the persistent memory, and the disk drives like the SSD. And the second part of today's talk, I will show something we have done between the CPU cache and the persistent memory. It's about the cache hit and the cache miss. So now let's first move to the first part, the I/O path. I guess everyone here, that we have two, we have two different types of I/Os. One is the asynchronous I/O, another one is the synchronous I/O. So actually one is just the buffered I/O. We use the normal I/Os, and the other one we use fsync or fdata sync. So let's use a very simple example here. We have this two lines of code. The first one, we just open a file, a text file, and with some flags, and then we write some data to this file. So let's see what will happen. So we have this application, it will write the data, and we have the DRAM page cache, and we have the SSD with the disk cache. And for the first option, for the flags, we can just use this ORDWR. That means we will use this ordinary buffered I/O, the asynchronous I/O to write data and write data. And we can consider just directly write the data to the SSD. So that means it will be the direct I/O. So of course, with this direct I/O, usually the data will write to the disk cache like the SSD cache. And we have the next option, which means we use the OSync. We can use the fsync or fdata sync. It depends. And here we just uniformly refer to them as the sync. So with this sync, the data will forcefully go into the persistent storage, like the flash here, the SSD. So we have different types of I/Os. Now let's see their performance. Let's compare their performance. We have done some tests with an ordinary SSD, And you can see this is the execution time when we write 4 GB and 8 GB with 3 different I/O types. And from the buffered I/O to the direct I/O, we can see the performance will drop by almost 10 times. And now if we use the F-Sync to write this data, the performance will further drop by another, less than 40%. So overall, the performance will drop from the buffered I/O to the synchronous I/O by about 13 times. So this performance drop is quite significant. So from this observation, we can get quite a straightforward observation. A conclusion is that, because why we use things like F-Sync, F-Data Sync, we just want to make the data orderly durable to the persistent storage like the SSD. So we must, use the F-Sync because F-Sync will provide 2 effects. The first one is just make the data persistent, so persist the data. Another one is F-Sync will work as a barrier. So later we will show for the LSM tree. So because we need this F-Syncs to make data orderly durable. But such F-Syncs, you can see it's quite heavyweight, it's quite costly, expensive. So is it possible to remove, at least some or most of the F-Syncs? We revisit this classical question, and we found that it depends on the applications. But for LSM tree, it's quite necessary. We must do that. Why? I guess today most of you have the background with the LSM tree. I just give a quick review. So for SM tree, we have the write request put to the mem table, and of course at the same time we will write the log, the write header log. And on disk, we will have multiple levels. So this will build a tree-like structure. And so when will we need the F-Syncs for the system, and why we need the F-Sync? Because when we put the write request, we just want to our key value pairs will stored into the persistent storage, and to build this to maintain this tree structure from time to time, we need the major compaction from the higher levels like L0 to L1, L1 to L2, L1 to L2. So to push the key value pairs to the lower levels. And during this building of the tree structure, we need frequently call the F-Syncs. As I mentioned, we need them to persist the data, and we also need them to behave like the write barriers, so orderly keep the data durable and consistent. So with this F-Syncs, because we need to frequently call the F-Syncs, so a very natural question for us for the LSM tree is that what LSM tree now has, as I mentioned, we have the multiple levels, and a very interesting observation is that LSM tree can give us some hint. We have the low levels. Actually, all the low levels, the SS tables at the low levels are coming from the higher levels. And L1 actually from L0, when you do the major compaction, you just merge from the L0 to the L1, L1 to the L2. So they have some dependency, like the dependency here. And we have a very interesting and during this process, they need the F-Sync. But let's assume that we keep the L0 SS tables synced. So we just sync the L0. So we can conclude that the Ln SS table should be also synced, because we have the data from the upper levels, and through the major compaction we can build the lower levels. And but now we see that once we sync L0, and we will have the Ln, but this is very tricky, because we know that only L1 is directly built from the L0. So we know L1 is now can rely on the L0. But how to do with the Ln? You know, n when n is even below than the L1, and also we cannot keep the L0 for forever. So we need sometimes we need to delete them to release the SSD space. So but LSM tree itself, it is an application. So by itself it cannot resolve this issue. So we need some help. We have the operating system. So because the LSM tree is working with the operating system to persist the data, so then whether we can leverage some feature of the underlying file system to remove the sinks for us. So this is what we consider for the LSM tree. So we turn to the underlying file system. And here, I guess we agree that today ext4 is still the widely used journaling file system for us. So our target is the ext4, and from the ext4 we find a very interesting feature of it is that when you make FS with the ext4 and when you build the ext4, you will mount it. When you mount the file system, you will have the default mode. Data is ordered. So this is data equals to ordered. So with this default mount option for the ext4, and we can have quite a interesting observation is that for this data is ordered, it will enforce a principle that the file data will be persisted before we commit the file's inode to the journal. So what does this mean? Let's use an example to illustrate this principle. So let's see, we have the ext4 file system. It will have two parts. One is the journal device. Another one is the file system. And let's see, we have a file. This file is it has an inode numbered 22, and it has the file data hello MSC 22. So it has the inode, it has the file data, and with this principle, data is ordered. So what we can have, we must first persist the data, file data to the file system, and then we will commit the inode to the journal. So this means what? This means if we can find that the inode is persisted, is committed to the ext4 journal, we can conclude the file data and the file's metadata, this inode, are both durable, are both persistent. So this gives a very good hint, because once we have the file data, we have the file's metadata. Now we have the whole file. So this is just achieves the same effect like the fsync. So we don't need to call the fsync if we can track whether the file's inode has been committed to the journal in the default data is ordered mode for the ext4. So this principle is kind of implicit, but it is very useful for LSM tree. Why? As I just mentioned, we have the major compaction of the LSM tree to build the tree-like structure. We have some, old SS tables. For example, here I just saw 4 SS tables, 2 of them from L0 and another 2 from L1. And we will merge sort the key value pairs inside them, and then we will repack the key value pairs to make the new SS tables. And during this process, we will by the very nature of the LSM tree, I mean the original LSM tree, it will fsync these new SS tables. After the fsync, they will remove the old SS tables. And as I mentioned, this fsync this new SS tables to make them persistent and persistently durable is very costly. But as I just mentioned, with the ext4 journaling, can we now, remove such everything? Of course we can, because we can just use the ext4 journaling to track and tell us what new whether new SS tables have been persisted. Whether their file data have been written to the file system, and whether their inodes. Actually, we just need to track their inodes. So we can use such tracking to replace the fsinks. So this is the main idea of what we have done in a paper published in DEC 2022. To track the commit of the inodes, we add some new system calls and structures in the ext4 file system. And overall, we modified and add about 200 lines of code. And if you know the ext4 has, I guess, 60,000 lines of code, this 200 lines of code is not so significant. And we just need to track the inodes and expose the commit, because we need to explicitly tell the LSM tree whether the inode has been committed or not. This is on the side of the ext4. And on the other side of the LSM tree, we also need to use such a commit, interface. So we modify and add about 130 lines of code in the level DB. This is a very typical LSM tree. And after this change, so we measured the new performance, and very, very luckily, we have the execution time almost halved with just about more than 300 lines of code over I guess more than 80,000 of lines of code altogether. And we didn't just measure the performance, we also with the real machine, and we also measure the consistency. We abnormally shut down the computer, the server for many times, and we can find that we achieve the same consistent level as the original level DB. So this work was actually the first author of this work was an undergraduate student of Shanghai Tech. Yeah, this is the first work we have done to explore the IO path in the ext4. And after this LSM tree, now let's move to another tree. Actually, Professor Hua Yu also mentioned this tree, the very classic B+ tree. And we want to plant another B+ tree in the persistent memory. And now, because we need the CPU cache and the PMEM, we need to load the B+ tree nodes to the CPU cache. Now the impact of the CPU cache is very important. So we need to consider how to make the most use of the CPU cache. So as the B+ tree, I guess here we all know it very well. The nodes of the B+ tree from the root to the leaves are well organized. But we just found that how to place such B+ tree nodes to the CPU cache has not been, thoroughly studied yet. So we just pay attention to this part, and we want to place them into the CPU cache with minimized cache misses. So first we need to justify, whether we need to do this, and we found that now today the cache miss is quite important for the B+ tree, especially with the upgrade of the architecture, because today's architecture has the new feature called EADR, extended ADR, which can provide the power loss protection. So the cache line flush, usually we use the cache line flush to flush the data from the volatile CPU cache to the PMEM, persistent memory. But now with the EADR, we do not need to do that. So without the CLWB, the cache line flush, and the performance contribution of the cache misses will increase. So with this one, this motivates us to study what we can do with the CPU cache and the PMEM. And we found that today our modern CPU just uses the VIPT cache. So what is a VIPT cache? We know that when we access the cache, we need the address. We need the address like this one. And with the VIPT cache, that means when we access the cache, we need to find the cache set. And the cache set, we can directly use the virtual address. We don't need to use any physical address. So using the virtual address, we can decide which cache set the data will go to. And if two data, they stay in different cache set, definitely they will have no conflict. No conflict means no conflict miss. So very simple. We just study this part. We find if for this segment, for this field, this 11 bits, if this means the set index, if they have different numbers, that means they will have different cache set index. So with this part, this 100, because together altogether this will have 17 bits, and we have 128 kilobytes. And then now with a typical B+3 node in 512 bytes, we can have this segment in 128 kilobytes, and this segment can hold 256 nodes, and all such nodes actually, because they have different set index, they will stay different cache set. So that means they will have no cache conflict. No cache conflict means no cache miss. So this is the idea we try to place the B+3 node by leveraging the implication of the VIPT cache. So with this idea, we repartition the PMEM space. Of course, we need some metadata and to manage this space. And then we have the segments. And when we allocate the B+3 node, we allocate from different segments, maybe from the same segment, because we have two main principles for allocation. The first one, we can have that if two nodes, if they allocated from the same segment, there's definitely no cache conflict. If even you allocate two nodes from different segments, they may have the likelihood of the conflict, but the conflict rate is very low. We have a measurement, it's about below 0.5% percentage. So this conflict rate is very low. So this is our proposal called a conflict-aware node allocation for the B+3, the Conan. And with this Conan, actually, we also do some experiments in the open source fast and fair, and we replace the PMDK, entire PMDK with our Conan, and we just modify about less than 80 lines of code. So just 70 to 80 lines of code. We measure the cache hit rate. We find that the cache hit rate can improve by 13%. And we also measure the performance with just 17 lines of code. We can boost the performance by about almost 20%. And this is running with the key value pair with the YCSB, the macro benchmark, the YCSB workloads. So this performance boost, because with such a small change, you can have quite a good performance. I think this is worthwhile doing. Okay, this is what we have done, by leveraging the implicit VIPT to boost the performance for the B+3. So now let me make a conclusion of my talk today. And today, I just saw what we have done to explore the implications from the memory and the storage. And you can see still there are many implications that have not fully exploited yet. And we just do some very simple attempts for the LSM tree and the B+3. Actually, currently we already find some more methods to further improvement, and we are trying our best to explore more, architectural implications. This work is done by our team, Toast Lab in Shanghai Tech. And thank you very much for your attention. Now I will be very glad to answer your questions. Thank you.
Thank you, Professor Wang. Let's see whether I have any questions from the audience. Actually, do we have any question from the offline? Maybe I have a very simple question. I think you have delivered very interesting ideas. For the second one, you mentioned the conflict-aware node placement, right? I wonder, because it's cache-related work, do you have any change in the hardware design, or you just modify the software level placement strategy?
Thank you for your question, Professor Zhou. This is a very good question. Actually, we just make use of the existing CPU. We don't do any change to the hardware. We just make use of it, and we find that it can give quite a good performance improvement. But this is a very good point that if we can further change at the hardware level, maybe we can have further improvement. Yeah.
Okay. Thank you. Thank you. Yeah. Any other questions? Okay, if not, thanks again. And we also have a certificate for you.
Thank you. Thank you.
Yeah.
This one.
Do I need to change it to the first page?
Yeah, you can go to the first page. We can we'll take a picture for this.
Yeah.
Okay.
Give me a second.
Yeah, okay. Sure.
Okay, thanks.
Thank you.
Thank you. Thank you.
Okay, thank you.
Thank you. So here comes our next talk. It's from Professor Weichen from Shandong University. He received the PhD degree from the Hong Kong Polytech University. His research interests include design, analysis, and optimization of real-time systems and intermittent computing systems. In the past 5 years, he has published more than 10 papers on the top conference and journals. He is also awarded 2012 CCF Huawei Popular Graph Fund. So welcome, Professor Chang.
Okay, thanks for the kind introduction, Professor Zhou. So my talk will be reducing backup overhead for intermittent computer systems. First, I will introduce some background of the intermittent computer systems. So it's predicted that the number of IoT devices will exceed 30 billion or even more numbers in the future years. So how to power such a huge number of IoT devices is a very challenging problem. Traditionally, we power such systems with a battery, but if we have a large number of IoT devices, this method is no longer suitable. So the energy harvesting is a promising technology to power such a huge number of IoT devices, as it can be, as it can harvest the energy from the ambient environment without maintenance. For example, replacing the batteries or recharging the batteries periodically. So energy harvesting is promising, but it also imposes some challenges on the software design. In terms of the premise and the progress program. The progress program is because that the energy harvested from the environment is generally weak and unstable. For example, we have shown some of the energy traces harvested from the solar panel. And we can see that sometimes the energy harvested from the solar panel is very weak, and it's often very unstable. So with this unstable and weak energy output of the energy harvester, the system may experience very frequent power failures. So this may cause a non-progress problem. This is because that every time the system experiences a power failure, it will reboot from the very beginning of the program. And therefore, when the power failure is very frequent, the system may repeat to reboot from the very beginning and cannot forward progress. So we have an example to show this phenomenon. For example, we have a program And if the system has a power failure, and then have enough power to execute again, the program will reboot from the very beginning, and then it will repeat from the very beginning again. So iteratively, the program cannot forward progress. So to solve the non-progress problem, the intermittent community system is proposed, which generally decomposes the program into a set of small program segments, and then back up the system states at the beginning of each segment. So benefited from the intermittent community system, when the system has a power failure and resumed again, the system can resume the system states from the latest program segments, and incrementally the system can forward progress. And we have an example to show this intermittent community system. For example, we have a program, and when the system has a power failure, and then it can continue execution from where it stopped. So incrementally, the system can forward progress and finally finish the execution. So this is the intermittent community system. But the problem of the intermittent community system is that it frequently back up the system states. So this leads to very significant backup overhead. And we have conducted some experiments, and the results show that in most cases, the backup can consume up to 95% execution time, which is significant. So how to reduce the backup overhead is a core research target in the research field of intermittent community system. And based on this observation, we have done some works on reducing the backup overhead. And in this presentation, I will introduce them one by one. The first work is an adaptive intermittent community system. So the behind idea of this work is that the energy harvested from the environment is not always unstable. So if the energy is sufficient, it is unnecessary to back up the system state so frequent. So based on this observation, we propose the adaptive intermittent community system, which can skip some backups when the energy is sufficient. For example, in the conservative system design, we back up the system state very frequent. Right? We back up the system state 4 times. But if at this time the energy is very sufficient, we do not need to back up so frequent, and we can use the adaptive execution, which can skip the backup before the task 2, task 3, and task 4, and therefore the program execution is improved. But adopting the adaptive execution is not a free lunch. So before introducing the challenge, I'd like to introduce the WR problem in the intermittent system. For example, the WR is a data access behavior, which if a variable is a WR variable, it means that it is a write after read variable. In the intermittent community system, at the beginning of each program segment, we should back up the WR variable of each program segment. For example, in task T2, we have a variable Z, and Z is a WR variable. Now, before the execution of T2, the value of Z is -1, and then Z is increased to 0 at this instruction. So if then we have a power failure during the execution of T2, and later it resumes from the beginning of T2, the value of Z is 0, which is increased in the previous power cycle. So this is incorrect. So to ensure the correctness of the execution, we should back up the value of Z at the beginning of the T2. So in generally, we should back up the WL variables of each task. So this is the WL problem. So let's back to our adaptive execution. The problem of the adaptive execution is that if we adopting the adaptive execution, it may create some new WL variables. This, for example, if we, in the traditional way, if we execute the task T1, T2, and T3 individually and back up the variables of each of them, we only back up Z at the beginning of T2. But if we observe that the energy is sufficient and we want to execute the task T2 and T3 together and skip the backup of T3, it may introduce the new WL variable, so which is X in this example. For example, X is only read at T2, but it is write at T3. So X is not a WL variable of T2 and T3. But if we execute T2 and T3 together, X is a new WL variable. So let's further imagine that if X is a large data structure, for example, an array with 1,000 elements, the adaptive execution may introduce a significant runtime overhead. So in our method, so due to this problem, in our method, we introduce to insert some breaking points to stop the adaptive execution when the new WL variable is created. So our system design is that we insert some breaking points and propose a WL analysis for the program. In the later, I will use the example to show how our method works. So firstly, we traverse the control flow graph of the whole program and analyze the possible WL variables of each leading tasks. And during the CFD traversing, we monitor the changing of the WL variables. And if the WL variables, sorry, the laptop is closed. So during the CFD traversing, we monitor the change of the WL variables. So if the WL changes dramatically, what means that a new WL variable is generated. We stop the CFD traversing and insert the breaking point. So this is performed at offline at compare time. And during the runtime, when the system encountering a breaking point, we stop the task classicity and enforcing the backup. So at the runtime, we also avoid the introducing of the new WL variable. Okay, and we have conducted some experiments to evaluate our method, and the results is obvious, and our work performed the best and different power traces. So this is our first work, which proposes an adaptive execution model to skip some backup overheads. And our second work is using the asynchronous DMA to parallelize the program execution with the backup to improve the efficiency. So let's revisit the state backup. So our first work is to adaptively change the backup frequency to improve the efficiency. But no matter how frequency is that, the state backup always performs sequential with the program execution, and which that the program should wait for the completion of the state backup and therefore the program is significantly blocked. So in this work, we try to propose the parallel backup to perform the state backup and the task in parallel, so that the latency of the backup can be hidden by the program execution. But the parallel, so this target can be achieved by some existing hardware in the current MCU, for example, the DMA, which can perform the data transfer without interrupt the CPU execution. But this may kill the data racing. For example, if we perform the backup and the program execution in parallel, for example, the variable A, the value of A will be increased to 2 by instruction 1 at time t1. And if we perform the backup in parallel, and the A will be backed up as 2 by the backup at t2. And if the system has a power failure at t3, and then resume the execution, the value of A is 2, as it is backed up as 2 at t2. So this may kill the correctness problem because of the data racing between the backup and the system execution. In our method, we propose a solution, which is that we firstly allow the incorrect backup to occur to improve the efficiency. And then we propose the error detection method and the fault tolerance backup management to ensure the correctness of the program execution in the process of the incorrect backup. So the first work is how to detect the incorrect backup. Before introduce our mechanism, let's think a problem of whether a variable is backed up correctly. So the answer is very simple, which is the variable is backed up before it is modified. And at this time, the variable is backed up correctly. But during execution, it is hard to build such a timing relationship between the modification and the backup of a variable. So in our method, we introduce some flags to build such timing relation. For example, we insert the modification to the flag before the modification to the variable. And we also back up the flag after the backup of the variable x. So after the backup, if the flag is backed up correctly, we can simply conclude that the backup of the flag is before the modification of the flag. And therefore, we can further build the timing relationship. The backup of x is before the modification of the x, so x is backed up correctly. So using this flag variable, we can build in the timing relation, and then we can test whether the backup is correct. Sorry for the format of this slide. So during execution, we do not need to insert each flag for each variable. This is because that first we only need to observe the WR variable. The second is that there are some redundant flags. For example, if we have a variable xc and d, and we want to insert the flags fc and d to detect the correctness of the backup of c and d individually. So we insert fc and fd. But during execution, actually we only need to insert the flag fc, as if fc is backed up correctly, fd must be backed up correctly. So fd can be simply removed, and we only need to keep fc so in our program. So we can optimize the error detection method. We also can reduce the backup errors by reordering the memory layouts of the variables. So the basic idea is that if the backup is earlier, it has less probability to to have conflict with the program execution. So it has a high probability to be backed up correctly. So we can reorganize the memory layout to reduce the backup errors. Okay, the second method of our system is that we propose the fault-tolerant backup management. So in the execution, this idea is quite simple, which is that we maintain another buffer to store the correct backup states. And when the system experiences port failure and then resume, we can always resume to the latest correct backup buffer, rather than the latest buffer of the traditional method. So this is the fault-tolerant backup management. And we also evaluated our method, and we show that for most benchmarks, the incorrect backup is the number of incorrect is very less. So this also demonstrates that we can allow the incorrect value to occur. This is because the number of incorrect values is very less. And most the incorrect backup are covered by the following backups. Okay, as the backups are performed very frequent, so we can allow the incorrect backup to occur. And for the system performance, we have shown that with different EVM speeds, our method performs the best compared with the sequential backup method. Okay, our last work is we use the SRAM data retention capability to reduce the backup. So the first two works focusing on the non-volatile main memory system architecture, but there are also many systems still use the volatile main memory in the MCU, and therefore they should to restore the VM data to the NVM before port failures. But we have found that in some existing MCUs, the minimum operating voltage of the MCU is much higher than the data retention voltage of the SRAM. For example, in the typical MCU MSP 430, the minimum operating voltage is 1.8 volt, but the SRAM data retention is 0.4 volts. So we can use this SRAM data retention capability to store the data on the volatile memory rather than copying to the non-volatile memory. And the challenge of this method is that we should validate the data on the volatile memory. This is because that we do not know how much time that elapsed during the power off. So we use CRC to validate the memory on the volatile memory, to validate the volatile data. And we have also optimized our method that we use the partial CRC to not fully validate the volatile data. So I will not go into detail of the partial CRC and due to the time limitation. And the experiment results show that since we can return data on the volatile memory and do not need to copy it to the non-volatile memory, the system overhead is significantly reduced. So that's our three works on reducing the backup overhead for intermediate computer systems. And in the future, we still have some targets to further reduce the backups, further improve the system performance of intermediate computer systems. So thanks for the attention. And
okay, thank you.
Yeah. And
so let's see. Yeah, if any question. Yeah.
Hello, Professor Zhang. I want to ask that in your second work, the parallel backup.
Yeah.
I noticed that there is a concept unrecoverable unrecoverable failure.
Yeah.
So what is unrecoverable fault?
So since the system performs the backup very frequent in intermediate system, we I'll use this slide to explain this problem. So since the backup is very frequent, so if we allow the incorrect backup to occur, it may be covered by the following correct backup, right? So if we allow the incorrect one to occur, as the system will continue to back up, and maybe laterally the incorrect backup may be covered by the correct backup. So we do not need to do anything, and since we have a correct backup, and we can correctly resume from the port failure. Yes.
Oh, and another question is about the optimization part.
Okay.
Yeah, you said we have FC and FD two flags. Why we can guarantee that FD is done if FC is done? I think it is that if FD is done, that we can guarantee that FC is done.
So the reason is that if a backup is correct, we need to guarantee that all the variables are backed up correctly. So if C is backed up correctly, but D is backed up incorrectly, this backup is also incorrect. So in this example, the FC can guarantee the correctness of FD. So we only need to we can simply remove FD. So if D is backed up, for example, if D is correctly, C is incorrectly, this is also incorrect. So we do not need to observe both of them. So yeah. Thank you.
Okay, thanks.
Hi, Professor Chang. I also have a small question.
Yeah.
I noticed for the third work you present that you state that the SRAM can store the data for seconds.
Yeah.
Maintain for second. So
yeah.
this is proved by any information or because in my mind I think SRAM cannot only maintain the data for very small time.
Yeah, it can only maintain data for very small time, maybe minutes, maybe seconds, or sometimes maybe minutes. But and this is also some empirical results. There is not some official data to prove this. So I'm sorry. What's your question is?
So this is proof that SRAM can maintain data for much longer time than the normal stated data.
Yeah.
Okay. Thank you.
Okay, thanks for the nice talk. So I think you can have your certificate in person.
Okay. Hello, Professor Zhang. I think it's time to give the thanks card.
My own.
Yes. Interview. Finally. Okay. I think you can do. Yeah. Good. And automate. Okay. Thanks for the offer.
No, thank you.
Okay, thanks to the speaker again. So we can move to the last talk today. It's from Dr. Mingxin Zhang. He is a tenure-track assistant professor at Tsinghua University. His research interests include the distributed system and modern hardware technologies. Results include more than 20 papers published on leading conference or journals, including OSDI, SOSP, S+, HPCA, VLDB, ATC, and so on. He has received the SIGSoft Distinguished Paper Award and Best Doctoral Award from IEEE TCSC and SingOps China. He got his PhD degree from Tsinghua University. So the talk of Professor Zhang is a novel programming framework for disaggregated architecture. Please welcome.
Thank you for the introduction. I'm Mingxin Zhang, an assistant professor from Tsinghua University. It is my honor to present our innovation on programming framework for a disaggregated architecture. So the audience may notice that there is currently a trend of building resource disaggregated architectures. It is a paradigm shift from servers that each tightly integrated with a small amount of various resources like CPU, memory, and storage to a disaggregated data center that is built as a combination of standalone resource blades and interconnected using a fast network fabric. Many works have been proposed to disaggregate almost everything in a modern data center. The benefits include more configurable and better utilization. This trend is motivated by recent developments of hardware technologies, especially remote direct memory access, also known as RDMA. According to the report, the newest generation RDMA network interface card can support more than 200 gigabytes per second bandwidth with an ultra-low latency, which is obvious a dramatic improvement of communication performance. On the other hand, RDMA is also well known for its capability of zero copy and kernel bypassing. Another important emerging hardware technology is non-volatile memory. It is blurring the line between memory and storage. These kinds of memories have provided DRAM-like performance and byte addressability. At the same time, NVM also provide high density and persistency. Thus, it is not a surprise that there are many works about how to combine RDMA and NVM in a disaggregated environment. Specifically, we conclude the existing works into 3 different architectures. Symmetric architecture is widely used in the existing distributed systems, in which each machine has its own NVM device, and hence it is not disaggregated. For achieving disaggregation, a straightforward implementation is use network-attached storage, which is also known as NAS. NAS can take advantage from the NVM over Fabric protocol to provide a shared NVM pool to the front-end nodes. However, NAS is heavily relied on the file system service in the storage node. It is based on the block access interface. As a result, the read and write amplification is not avoided, cannot be avoided if only fine-grained data access is needed. And fine-grained data accessment is very necessary if we want to build remote data structures in the NVM pool. So to overcome the problem of NAS, we propose the asymmetry NVM architecture, where NVM devices are not associated with the individual machine. They are served by specialized NVM blades and accessed at byte level, only passively via fast RDMA network. In asymmetry NVM architecture, the number of NVM devices can be much smaller than the number of compute machines. Compared to the symmetric architecture, asymmetric NVM offers 4 advantages. First, it enjoys the benefits of disaggregation. Second, it naturally matches the desire of sharing large NVM to many front-end computer nodes. Third, it ensures availability with multiple backends. And fourth, the backend nodes can be implemented in a very simple manner that leads to better reliability. So this table illustrates the API sets provided by our asymmetry NVM framework. The first set of APIs provided a transactional interface that allows the front-end nodes to push a list of update logs to the backend to achieve persistency and atomicity. The second set of APIs handles memory management procedures, such as remote memory allocation and remote memory releasing. The third set of APIs deals with concurrency control. In our system, we provide single writer but multiple reader concurrency control support. So as an illustration, here we present an example that uses our asymmetry NVM framework to implement the insert operation of a remote skip list. The program first allocates the insert position by using multiple remote NVM read operations. Then it allocates remote NVM resources and flushes one high-level operation log to the backend immediately for persistency and recovery, which only records this insert operation and not the detailed memory accesses. Next, the framework appends low-level memory log to the front-end buffer in the local DRAM. And finally, these buffered memory logs will be flushed to the backend NVM to modify the real data of this skip list. So according to our investigation, in order to provide high efficiency for the above set of APIs, we face three main challenges. The first challenge is network latency. Although the bandwidth of InfiniBand is comparable to NVM, the latency is not. RDMA operation RTT is about 2 microseconds, which is much larger than the latency of accessing NVM directly. Simply replacing local operations with RDMA operations will significantly degrade the performance. The second challenge is how to efficiently use the small volatile space of the front-end nodes. The high density of NVM devices make it capable of holding terabytes of data, but the memory space of a typical front-end node is only tens of gigabytes. This asymmetry implies that the system should only catch necessary data in the current work set into the front-end nodes during the execution. The third challenge is the design of the backend interface that should be both effective and simple with good reliability. Specifically, backend, we assume that this backend should only be responsible for performing a small collection of very simple APIs, such as remote memory read, remote memory write, and allocation or releasing. The solution to the above three challenges centralized to our log-based design. In our system, there are two kinds of logs, one high-level operation log and one low-level memory log. Instead of directly writing to the backend memory, which will have very high latency, every update operation in the front-end data structure will generate several memory logs that records the memory address of the modified place and the updated value. The backend node provides a simple transaction API called remote NVM transactional write to ensure that a collection, or we call it a transaction of memory logs, will be persistent atomically in an all or nothing manner. To implement this API, asymmetry NVM framework constructs a continuous set of memory logs and appends to the corresponding log area at the remote NVM via a single RDMA write operation. This format of these memory logs is demonstrated in the slide. The other log is operation log that only records what operation is performed and the corresponding input parameters of this operation in the log. The crucial benefit of using this operation log instead of using only the memory log is that if we use this operation log, we can enable batching and caching. Once the operation logs are recorded in the NVM, the following detailed modifications on the real data structures can be postponed and batched to improve the performance. Even after a crash, the state of the remote NVM can be restored by replaying the operation logs. In short, memory log is a low-level log without data structure semantics and will be used by the backend to reply the detailed updates on persistent data structures. The flushing of memory logs can be postponed and batched to improve the throughput. In contrast, the operation log is synchronized flushed once every operation is performed on the front-end data structure. This is a high-level log with data structure operation semantics that is only used for recovery. So this figure demonstrates the high-level workflow of asymmetry NVM, which use the aforementioned two kinds of logs. In the read path, or we call it in the gather phase, the system of asymmetry NVM will first try to fetch the data from the front-end cache. If the catch not hit, the data will be read from the backend directly, or we can read the corresponding page and swap in and put the removed page into the catch. The choice between these two strategies depends on the specific data structures and following a principle that we will swap in the whole page if it is located in the hot data, and we will just directly remote read the data if it is located in the cold data. In the write path, or we call it in the apply phase, each modification operation causes one operation log to be flushed to the backend for recovery. While flushing this log, the catched data can be modified concurrently and continuously generating memory log in local DRAM buffer. So this is in local DRAM buffers and avoid the remote memory accesses. So if a number of operations have been executed successfully, all this local buffer is full, the buffered message logs will be flushed to the remote NVM with a batched manner. So these logs are then handled by the backend and replicated to other minor nodes for achieving high availability. So similar to other works, the front end manages a hash map to translate the address of the data structure nodes in the remote NVM to the address in the local DRAM. Our catch replacement policy combines the methods of ALRU and the random replacement. In fact, we use a hybrid approach. We first choose a random set of pages for replacement, and then we selecting a least used page from this set to discard. At the backend, we implement NVM management APIs using our former work called RPC. And to ensure persistency, we use a persistent bitmap to record the usage blocks of NVM in the remote NVM. And hence, a pointer to the backend NVM will be still valid after a restarting of the front-end node. So we also use a global naming space in the backend NVM for recovery. The metadata will be stored in well-known locations for all the front-end and the backend nodes. So we can use a hash map to index those critical metadata, and each item in the hash map contains the type, the name, and the physical address of this item to easily recover the data after a restarting. In addition, we leverage the RDMA atomic verbs compare and swap to implement a writer log for single write and multiple read concurrency control. To handle the failures while holding the log, every log acquirement or log releasing will write an operation log first to the backend, and since after restarting, we can use these logs to recover the log statement. Our design can be divided into log-based and log-free data structures. For log-based data structures, we implement retry-based optimistic read logs by using a sequence number. For log-free data structures, it will benefit the reader, but needs to create multiple copies by the writers to enable the log-free data accessment. For log-based data structures, it prioritizes the writer without using the extra copies, but the readers will need to read multiple times until it reads consistent data. The right choice between to use log-free or log-based data structures is depend on the specific applications. We use key hashing partition to eliminate the potential bottleneck due to the log and achieve both high throughput and better scalability. Each partition has its own write log and index data structure. These mapping tables between key range and partition are also stored in the former mentioned global naming space, so it can be recovered after a restarting. The underlying APIs of asymmetry NVM is general, and it can be used to implement various data structures. But we also propose data structure-specific optimizations. For example, in tree-like data structures, the nodes in higher level are more frequently accessed than the lower level nodes. So we choose to catch higher level nodes with higher priority. so we can have a better catch-hit ratio. So at the end of this talk, we will present our evaluations from several aspects. As we can see from this slide, our optimized implementation can provide nearly 5 times to 12 times improvements compared to the naive implementation, which access the remote NVM directly using RDMA read and write without any optimizations. We implement several very useful data structures such as the B tree, the hash map, and the skip list. And all these data structures can be optimized by our framework. We also measure the throughput of multiple front ends sharing only one NVM, so we can share the density NVM with multiple front ends. And the results show that the scalability is almost linear. We also measure the performance of batching with vector operations under different batch sizes. As we can see from the result, multi-version data structures, which is used for the lock-free data structures, typically have lower improvement because of path copying. But if we enabling the batching, this batching mechanism can effectively reduce such overhead. We also measure the benefit of catching under different catch sizes. In conclusion, the throughput of our fine-grained remote data structures will increase dramatically when we increase the catch size. And it is obvious because the a larger catch size means that a higher catch hit ratio. So we also use YCSB to the YCSB tool to generate a skilled workloads, and we also use an industry workloads from an online service of Alibaba. This industry workloads trace the real-world application behavior and is satisfied both the power law distribution. And the results also show that asymmetry NVM performs very good under this industry workloads and the skilled workload. So that's all of my presentation, and thank you very much. I'm welcome for any questions.
Okay, thank you, Professor Chang. Let's see whether we have some questions from the audience. Okay, maybe I have a simple question. You have mentioned your evaluation is proved that the scalability is very good, right?
Yes.
So can you comment that what happens if we include more and more such kind of NVM nodes? Would the performance or the energy will be highly affected? And what happens if we have a large number of nodes and we have heavy workloads? Can you comment on this?
Okay, thank you for the question. It's a very good question. In fact, there are two kinds of scalability. In this slide, we report the scalability by sharing one backend NVM node with multiple front-end nodes. And as we can see from the result, the performance increase almost nearly by increasing the number of front-end nodes. But there will be a bottleneck at the backend nodes if we congest the RDMA NIC of the backend nodes. In this case, we can also scale out the backend node for even better scalability. And we have mentioned in this slide that we use key hash partitioning to scatter the specific region of the memory to different backend nodes. So combining these two kinds of scalability, we can enjoy a very high scalability. So
okay, thank you. Any other questions? Okay, if no more questions, I ask Professor Shi to give the certificate.
Right. Okay. Okay. Very thanks to Professor Chang. Okay. Maybe let us ask Professor Weichen. Okay. We prepared a thanks card for you, and this will be transferred to you.
Thank you. Thank you, Professor.
Okay. And lastly, we also have hello, Professor Chang. We have a excellent program chair certification
Thank
for
you.
Professor Chang. And where is Professor Chang? Can you fix the big picture here?
How can I fix the picture?
Yes, the last thing is the
you can remove
double click.
Double click.
Yes.
Okay. Okay.
Okay, thank you.
This is, yeah, this year we have a program tier. Okay, I will transfer this one to you. Okay. Okay, I think this is the end of the first half day program, and our workshop has the most number of attendees offline and online. So please become here tomorrow for the second half day, and Professor Zheng from Flux will do a brief presentation tomorrow. So online, offline, come here tomorrow. Thank you. Thank you. This is the end of the first half day.